Welcome to today's problem walkthrough. We'll be solving problem number 1294, titled Weather Type Counts. In this problem, we'll explore how to analyze weather data and count occurrences of specific weather types efficiently. Get ready to dive into the details and sharpen your problem-solving skills. In this problem, you're tasked with analyzing weather data from a list of records. Each record is a string representing a weather type, and it can only be one of four options: sunny, rainy, cloudy, or snowy. Your goal is to determine how many times each weather type occurs and return these counts in a dictionary. For example, if the input list is sunny, rainy, sunny, cloudy, the output would be a dictionary like sunny, 2, rainy, 1, cloudy, 1, snowy, 0. Notice that even if a weather type doesn't appear in the input, it must still be included in the dictionary with a count of 0. This ensures that all four weather types are always represented in the output. Now let's look at some examples to better understand the problem. In the first example, the input list is sunny, rainy, sunny, cloudy, sunny, snowy. When we count the occurrences of each weather type, we find that sunny appears 3 times, rainy appears once, cloudy appears once, and snowy appears once. Using this information, the output dictionary is sunny, 3, rainy, 1, cloudy, 1, snowy, 1. This dictionary accurately reflects the count of each weather type in the input list. In the second example, the input list is snowy, snowy, rainy, rainy, rainy. Here, sunny and cloudy are not present, so their counts are 0. Meanwhile, rainy appears 3 times and snowy appears 2 times. This leads to the output dictionary: sunny, 0, rainy, 3, cloudy, 0, snowy, 2. Another scenario to consider is when the input list is completely empty, as shown in the third example. With no weather records in the list, all four weather types have a count of 0, resulting in the output: sunny, 0, rainy, 0, cloudy, 0, snowy, 0. These examples highlight the importance of ensuring that the output always includes all four weather types, even if some of them have no occurrences. Now let's review the constraints and edge cases for this problem. The size of the input list weather can range from 0 to 10,000, so any solution must handle large inputs efficiently. Each string in the input list will always be one of the four valid weather types: sunny, rainy, cloudy, or snowy. Importantly, the output dictionary must always include all four weather types, even if some of them have a count of 0. For example, in the edge case where the input list is empty, the output must still include all weather types with a count of 0. Another edge case is when all four weather types are represented exactly once, such as in sunny, rainy, cloudy, snowy. In this case, the output should show a count of 1 for each weather type. These constraints and edge cases ensure the function behaves predictably across a variety of scenarios. Finally, consider the edge case where only one weather type dominates the input list. For instance, if the input is sunny, 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 the output should be sunny, 3, rainy, 0, cloudy, 0, snowy, 0. This demonstrates that even when only one weather type is present, the output must still include all other weather types with a count of 0. Additionally, the solution must be optimized to handle up to 10,000 records efficiently, ensuring it can process large datasets without performance issues. By adhering to these requirements and including all weather types in the output, the problem guarantees a consistent and predictable result regardless of the input size or composition. To start, one straightforward way to solve this problem is by using a brute force approach. The intuition here is simple: manually iterate through the list of weather records and count how many times each type of weather appears. To implement this, we initialize 4 separate counters, one for each weather type, such as sunny, rainy, cloudy, and snowy. As we loop through the list, we examine each entry and increment the corresponding counter based on its value. This method is highly intuitive and doesn't require any additional data structures. In terms of complexity, the time complexity is O(n), where n is the size of the list, and the space complexity is just O(1), since we maintain only 4 variables. While this method is simple and gets the job done, it has some limitations, particularly when it comes to scalability if the number of weather types increases significantly. However, the brute force approach does come with notable disadvantages. The code can become verbose and increasingly difficult to manage if new weather types need to be added. It isn't flexible for dynamic input types and requires manual updates whenever changes occur. To address these challenges, we can use an optimized approach based on dictionaries. Instead of manually maintaining separate counters, we leverage the dynamic nature of dictionaries to count occurrences of each weather type. The key here is that dictionaries allow for efficient storage and updating of key-value pairs, making them an excellent fit for this problem. In this approach, we start by creating an empty dictionary. As we iterate through the list, we check whether the current weather type already exists as a key in the dictionary. If it doesn't, we add it with an initial count of 1. If it does exist, we simply increment its count. By the end of the iteration, the dictionary will dynamically store the counts for all weather types, making this method more concise and scalable. Examining the complexity of the dictionary approach, we see that the time complexity remains O(n), just like the brute force method, since we still need to traverse the entire list of weather records. However, the space complexity is O(k), where k is the number of unique weather types. In this specific problem, k is constant because we only have 4 weather types, but this approach is still highly adaptable to other scenarios with more categories. The dictionary approach offers several advantages, such as being more concise and maintainable. It is also easily extensible if new weather types are introduced, as no manual initialization is required. Additionally, it dynamically handles inputs without needing to hardcode specific weather types. On the downside, this method does require some understanding of how dictionaries work and uses slightly more memory than the brute force approach. Still, for most use cases, this trade-off is negligible given the scalability and clarity it provides. For an even more streamlined solution, we can consider using Python's collections counter. The collections counter module provides a specialized tool for counting objects, simplifying the task even further. Instead of manually creating and updating a dictionary, we can use this built-in functionality to handle the counting process for us. To implement this, we import counter from the collections module and pass the list of weather records to it. In a single step, counter generates a dictionary-like object where the keys are the unique weather types, and the values are their respective counts. The time complexity remains O(n), as the list still needs to be traversed, and the space complexity is O(k), where k is the number of unique weather types. The primary advantages of counter are its simplicity and efficiency. It allows for the cleanest, most concise implementation, leveraging Python's built-in capabilities. However, it does require importing an external module, and for beginners unfamiliar with counter, the syntax may seem less intuitive at first. Despite this, it's an excellent tool for solving this type of problem with minimal effort. Among the approaches discussed, the optimized dictionary-based strategy was chosen as the primary solution. This method strikes the perfect balance between simplicity, efficiency, and scalability. While collections counter offers a slightly more concise option, the dictionary approach avoids the need for additional imports and provides more control over the counting process. In contrast, the brute force method, although functional, was set aside due to its verbosity and lack of scalability. Several key observations guided this decision. First, dictionaries are inherently well-suited for dynamically managing key-value pairs, making them perfect for counting occurrences without requiring prior initialization. Second, this approach is generalizable, meaning it can handle any set of weather types without needing to modify the code. Finally, while counter is a powerful tool, the dictionary approach delivers nearly identical functionality with minimal extra effort, making it a pragmatic choice for this problem. The dictionary-based approach stands out as the ideal solution for several reasons. In terms of efficiency, it achieves O(n) time complexity while keeping space usage minimal. Its readability ensures that the code is clear and easy to understand, even for those who might be new to the problem. Additionally, it is highly scalable, adapting seamlessly to changes in the set of weather types without requiring manual adjustments. Of course, there are trade-offs to consider. While counter provides the shortest implementation, the dictionary approach avoids dependencies on external imports, which can be a subtle advantage in some contexts. Similarly, although the brute force method has slightly lower memory usage, it sacrifices flexibility and readability, which are crucial for maintainable code. In summary, the dictionary-based approach offers the best combination of performance, simplicity, and adaptability, making it the most effective solution for this problem. To solve the problem of counting weather types, we begin with a straightforward approach. Imagine you're given a list of weather records containing entries like sunny, rainy, cloudy, and snowy. The task is to count how many times each of these weather types appears in the list. To achieve this, the first step is to set up counters for each type: sunny_count, rainy_count, cloudy_count, and snowy_count, all initialized to 0. Next, we iterate through the list, examining each weather record one by one. For every record, we use conditional statements to check its type. For example, if the record is sunny, we increment the sunny_count by 1. Similarly, if it's rainy, we increment the rainy_count. This process ensures that every record is evaluated, and the corresponding counter is updated accordingly. The same logic applies for the remaining weather types. When we encounter a cloudy record, the cloudy_count is increment, and for snowy, the snowy_count is updated. After processing all the records in the list, the final step is to return the counts for each weather type in a structured format, such as a dictionary. This method is efficient, with a time complexity of O(n), where n is the number of records in the list. Every record is processed exactly once. However, we should also consider edge cases. For instance, if the input list is empty, the counters will remain at 0, which is the expected behavior. Additionally, we need to handle invalid records, entries that don't match any of the 4 weather types. These could either be ignored or trigger an error, depending on the problem requirements. Another potential challenge is handling case sensitivity. If the weather types in the input are not consistently capitalized, we can normalize them by converting all strings to lowercase before comparison. For maintaining the counts, simple integer variables like sunny_count and rainy_count work perfectly since there are only 4 fixed weather types. These variables allow constant time updates, making the solution both efficient and straightforward. However, for added flexibility, we can use a dictionary to store the counts. For example, a dictionary like sunny 0, rainy 0, cloudy 0, snowy 0 can be used to dynamically manage the weather types and their counts. This approach also makes it easier to handle scenarios where new weather types might be introduced in the future, as we can simply add new keys to the dictionary without changing the core logic. To further optimize the solution, pre-processing the input list to ensure consistent formatting, such as converting all entries to lowercase, is helpful. Additionally, encapsulating the counting logic in a function makes the solution modular, which simplifies testing and integration. Now, let's walk through an example to see this algorithm in action. Suppose the input list is sunny, rainy, cloudy, sunny, snowy, rainy, sunny. We start by initializing all counters: sunny_count equals 0, rainy_count equals 0, cloudy_count equals 0, and snowy_count equals 0. As we iterate through the list, the first record, sunny, increments sunny_count to 1. The next record, rainy, increments rainy_count to 1. Then, cloudy updates cloudy_count to 1. The fourth record, another sunny, increases sunny_count to 2. Snowy increments snowy_count to 1, followed by another rainy, which updates rainy_count to 2. Finally, the last record, sunny, brings sunny_count to 3. After processing all the records, the final counts are stored in a dictionary: sunny, 3, rainy, 2, cloudy, 1, snowy, 1. This dictionary is returned as the output, providing a clear and concise summary of the weather type counts. This Python implementation solves the problem of counting the occurrences of specific weather types in a list of weather records. Let's walk through the code step by step. First, we define a method countWeatherTypes inside the solution class. This method takes a single argument, weather_records, which is a list of strings representing the weather conditions. The goal is to count the occurrences of each weather type: sunny, rainy, cloudy, and snowy. We begin by initializing a dictionary named counts. The keys are the weather types, and the initial values are all set to 0. This dictionary will serve as our accumulator for the counts of each weather type. Next, we iterate through the weather_records list using a for loop. For each weather condition in the list, we check if it exists as a key in the counts dictionary. If it does, we increment its corresponding value by 1. This ensures that we only count valid weather types and ignore any unexpected values. After processing all the records, the dictionary counts contains the final counts for each weather type. The method returns this dictionary as the result. An example usage is provided in the main block. We create an instance of the solution class and call the countWeatherTypes method with a sample list of weather records. The output is printed, showing the counts for each weather type: sunny, 3, rainy, 2, cloudy, 1, snowy, 1. This implementation is efficient and straightforward. It processes the input list in O, N, time, where N is the number of weather records. The space complexity is O1, as the dictionary size remains constant regardless of the input size. The code is robust and handles edge cases such as an empty input list or unexpected weather types gracefully, as the iteration simply skips over unrecognized weather conditions. Here, we start by importing the necessary Java utilities and defining our solution class. Inside this class, we have the method countWeatherTypes, which takes a list of weather records as input. The goal of this method is to calculate how many times each weather type appears in the list. To do this, we first initialize a hash map called counts, with keys representing the weather types sunny, rainy, cloudy, and snowy, and their initial values set to 0. This ensures that we start counting with a baseline for each type, even if a particular type doesn't appear in the records. Next, we iterate over each weather entry in the given list. For every weather type found in the map, we increment its count by 1. This is achieved using the containSKey method to check if the current weather exists in the map, followed by updating its value using the put method. Finally, the method returns the populated counts map, which now contains the tallies for each weather type. In the main method, we test the functionality of the countWeatherTypes method. We start by creating an instance of the solution class. Then, we define a sample list of weather records, which includes various occurrences of sunny, rainy, cloudy, and snowy. This list is passed to the countWeatherTypes method, and the resulting map of counts is stored in the variable result. To verify the output, we print the result to the console. The output shows that sunny appears 3 times, rainy appears twice, while cloudy and snowy each appear once. This demonstrates that the method successfully counts the occurrences of each weather type and handles a mixture of inputs correctly. In this example, we start with an input array of weather records containing a mix of weather types: sunny, rainy, cloudy, and snowy. The method countWeatherTypes is called with this input, and the first step is to initialize a dictionary named counts. This dictionary has keys for all possible weather types: sunny, rainy, cloudy, and snowy, and each key is initially set to 0. At this stage, the dictionary looks like this: sunny, 0, rainy, 0, cloudy, 0, snowy, 0. Once this setup is complete, the method proceeds to iterate through the input array. For each weather record, it checks if the weather type exists in the counts dictionary. If it does, the corresponding value is incremented by 1 to keep track of how many times that weather type has appeared. The iteration begins with the first weather record, which is sunny. Since sunny exists in the counts dictionary, its value is incremented from 0 to 1. The updated state of the dictionary becomes sunny, 1, rainy, 0, cloudy, 0, snowy, 0. Next, the second record, rainy, is processed. The count of rainy is increased from 0 to 1, resulting in sunny, 1, rainy, 1, cloudy, 0, snowy, 0. The third record is cloudy, which also exists in the dictionary. Its count is incremented from 0 to 1, and the updated state is sunny, 1, rainy, 1, cloudy, 1, snowy, 0. When the method encounters the fourth record, sunny again, the count of sunny is further incremented from 1 to 2. The dictionary now reads sunny, 2, rainy, 1, cloudy, 1, snowy, 0. The process continues with the fifth record, snowy, which increases from 0 to 1, making the state sunny, 2, rainy, 1, cloudy, 1, snowy, 1. Finally, the sixth record, rainy, is processed, increasing the count of rainy from 1 to 2. At this point, the dictionary becomes sunny, 2, rainy, 2, cloudy, 1, snowy, 1. The iteration concludes with the seventh and final record, which is sunny. The count for sunny is incremented 1 last time, going from 2 to 3. This brings the final state of the counts dictionary to sunny, 3, rainy, 2, cloudy, 1, snowy, 1. After processing all the records, the method returns this dictionary as the result, providing the frequency of each weather type in the input array. This structured breakdown makes it easy to understand how often each type of weather occurred. Moving on to another example, we'll see how the method handles input where only one weather type is present. In this second example, the input consists entirely of the weather type rainy, repeated 3 times. Once again, the method initializes the counts dictionary with all weather types set to 0, sunny, 0, rainy, 0, cloudy, 0, snowy, 0. Then, it begins iterating through the input array. The first record is rainy, and the corresponding count in the dictionary is increment from 0 to 1. The updated state becomes sunny, 0, rainy, 1, cloudy, 0, snowy, 0. The second record is also rainy, so the count for rainy increases from 1 to 2, resulting in sunny, 0, rainy, 2, cloudy, 0, snowy, 0. Finally, the third record, again rainy, increments the count from 2 to 3. The final state of the dictionary is sunny, 0, rainy, 3, cloudy, 0, snowy, 0. With the iteration complete, the method returns this dictionary as the result, showing that only rainy was present in the input. Now, let's consider an example where the input includes some unrecognized weather types. The input array contains sunny, stormy, sunny, rainy, and blizzard. The method starts by initializing the counts dictionary as usual: sunny, 0, rainy, 0, cloudy, 0, snowy, 0. The iteration begins with the first record, sunny, which is recognized. The count for sunny is increment from 0 to 1, making the state sunny, 1, rainy, 0, cloudy, 0, snowy, 0. Next, the second record is stormy, which is not a recognized weather type. Since it doesn't exist in the counts dictionary, it is skipped, and the state remains unchanged. The third record, sunny, is recognized again, so the count for sunny increases from 1 to 2. The updated dictionary becomes sunny, 2, rainy, 0, cloudy, 0, snowy, 0. The fourth record is rainy, a recognized type, and its count is increment from 0 to 1. Finally, the fifth record is blizzard, which, like stormy, is not a recognized weather type. As a result, it is skipped, and the state of the dictionary remains unchanged. The final state of the counts dictionary is sunny, 2, rainy, 1, cloudy, 0, snowy, 0. After processing all the records, the method returns this dictionary as the result. This example demonstrates how the method effectively ignores unrecognized weather types while accurately counting only the recognized ones. By handling these different scenarios, the method ensures that the output remains reliable and focused on the specified weather categories. Here, we're analyzing the time complexity of the countWeatherTypes function. The function begins by initializing a dictionary, counts, with keys for specific weather types and their values set to 0. This setup is a straightforward operation that always involves the same fixed number of keys, so its time complexity is constant, or O1. Once the dictionary is ready, the function proceeds to iterate over the weather_records list. If the list contains n elements, the loop processes each element individually. For each weather type, it checks if the key exists in the dictionary and increments the corresponding count. Both the dictionary lookup and the increment operation are performed in O1, time on average, meaning each record is processed in constant time. When you multiply this by the total number of records, the loop has a time complexity of O(n). Finally, at the end of the function, returning the dictionary is another O1 operation since it doesn't involve any additional processing. When we sum up all these components, the overall time complexity of the function is O(n). To summarize, the time complexity consists of 3 main parts: O1 for initializing the dictionary, O(n) for iterating through the list, and O1 for returning the dictionary. Adding these together gives an overall time complexity of O(n), where n is the length of the input list. Now let's look at space complexity. The space required by the function is primarily determined by the dictionary counts. This dictionary has 4 fixed keys, one for each weather type and their associated values. Since the number of keys does not depend on the size of the input, the space required for the dictionary is constant, or O1. Additionally, the function does not create any copies of the input list or use any extra data structures that depend on the size of weather_records. The loop itself only uses a constant amount of space for its iterator variable. Therefore, the overall space complexity of the function is O1, as the memory usage does not scale with the size of the input. With this understanding of time and space complexity, let's compare this approach to a more naive method. A brute force solution might involve counting each weather type separately by iterating through the weather_records list multiple times. For instance, you might use the count method to determine how many times sunny appears, then repeat this for rainy, cloudy, and snowy. In this case, each weather type requires an O(n) iteration, and with 4 weather types, the total time complexity becomes O for *n, which simplifies to O(n). While the time complexity matches the optimized solution, the naive approach involves multiple passes over the data, leading to higher constant overhead and making it less efficient in practice. By contrast, the optimized solution processes the input in a single pass, achieving the same O(n) time complexity while minimizing unnecessary overhead. This single-pass approach is both faster and more resource efficient. Let's now analyze the best, average, and worst-case scenarios for this function. In the best case, all weather records are valid and present in the dictionary. Here, the loop processes each element exactly once, and the time complexity is O(n). In the average case, some weather records might be invalid, meaning they don't match any of the predefined keys in the dictionary. However, since dictionary lookups are still O(1), the loop's time complexity remains O(n), despite these invalid entries. Even in the worst case, where all weather records are invalid, the function still iterates through the list of size n and performs O(1) checks for each element, so the time complexity doesn't change, it remains O(n). Mathematically, the function performs one O(n) loop and a few O(1) operations, summing up to O(n) overall. Finally, because the only additional memory usage comes from the fixed-size dictionary, the space complexity remains O(1) in all cases. When solving this problem, there are several common mistakes to watch out for. First, forgetting to test with edge cases can easily lead to bugs. For example, you might overlook what happens if the input list is empty, contains only one weather record, or if all the records are identical. These scenarios often expose gaps in logic that need to be addressed. Another frequent issue is implementing an inefficient solution. For instance, using nested loops with O(n)² complexity instead of a more efficient O(n) approach with a hash map can cause time limit errors on larger datasets. It's also important to consider case sensitivity and formatting. If weather records are stored as strings, failing to standardize the case or trim whitespace could produce incorrect results. Additionally, hard-coding values, such as assuming a fixed number of weather types, makes your solution less flexible and prone to failure with dynamic inputs. Finally, be cautious not to modify the input list directly. Actions like in-place sorting can lead to unexpected side effects, especially if the original data is needed later in the program. Now, let's delve into some key interview insights that can help you approach this type of problem effectively. Recognizing patterns is crucial. For example, many problems involving counting or frequency can be solved efficiently with hash maps or arrays. Spotting this pattern early can save you a lot of time. It's also helpful to start with a brute force solution to fully understand the problem, then refine and optimize your approach. For instance, instead of iterating through the data twice, once to count and once to process, you can often condense this into a single pass for better performance. Additionally, in an interview setting, clear communication is vital. Always explain your reasoning, particularly when choosing data structures. For example, you might justify using a hash map by pointing out its average O(1) lookup time. To deepen your understanding, you can explore related problems like toSum, which relies on efficient lookups with a hash map, or first unique character in a string, which emphasizes counting frequencies. Problems like sort characters by frequency and majority element are also excellent for practicing similar concepts, as they build on the idea of counting and processing data efficiently. Alternative approaches can also be valuable when solving this problem. For example, instead of using a hash map, you could sort the input list and then count consecutive elements. While this method has a higher time complexity of O(n) log n, it might be simpler to implement in certain cases. Another option is using a divide and conquer approach. This involves splitting the list into halves recursively and combining results, which can be effective for specific scenarios, like finding the most frequent element. For massive datasets, such as weather logs too large to fit in memory, streaming algorithms become useful. These methods use limited memory to approximate frequencies, making them well-suited for large-scale problems. However, each approach comes with its trade-offs. For instance, while hash maps provide O(n) time complexity, they require additional memory, whereas sorting reduces space usage at the cost of slower O(n log n) performance. You also need to consider whether to pre-process data or compute results on demand. Pre-processing frequencies allows for faster queries later but increases initial computation and memory usage. On the other hand, computing results on demand saves memory but can slow down repeated queries. Weighing these trade-offs is key to choosing the most appropriate solution for your specific constraints. Thanks for sticking around. Today, we learned how to tackle the weather type counts problem using a brute force approach. Remember, starting simple often helps uncover deeper insights and leads to better optimizations. Keep practicing, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!